When you look up at the night sky, scattered with silent points of light across an almost unbearable darkness, have you ever allowed yourself to ask a question so simple that it becomes dangerous? What does it mean for something to exist at all? Not stars, not galaxies, not atoms or particles, but existence itself. Why is there something rather than nothing? This question appears innocent, almost philosophical, but the moment we take it seriously, it begins to destabilize everything we think we understand about reality. Because embedded inside it is an assumption so deep that we rarely notice it. We assume that nothing is a valid starting point. That there could have been a state where absolutely nothing existed, and from that emptiness, somehow, everything emerged. But here is where we must pause and examine the foundation beneath our thinking, because modern physics does not allow this assumption to stand. The idea of nothing, as it is commonly imagined, a complete absence of space, time, energy, structure, law, turns out not to be physically meaningful. It is not just unlikely. It is undefined. And once we begin to see why, the entire narrative of the universe changes direction. To understand how radical this shift is, we must briefly return to a time when the universe seemed far simpler. In the worldview of Isaac Newton, space and time were absolute. They existed as a fixed stage upon which matter moved, unaffected by the actors themselves. You could, at least in principle, remove all matter from the universe, and what remained would still be space and time, stretching infinitely in all directions. In that picture, nothing seemed almost intuitive. Just take everything away, and what you have left is empty space. But this comfortable intuition did not survive the 20th century. When Albert Einstein re-examined the nature of space and time, he found something deeply unsettling. Space and time are not passive backgrounds. They are dynamic, malleable, intertwined into a single entity we now call space-time. Matter does not simply move through space-time. It shapes it, and space-time, in turn, dictates how matter moves. This means something profoundly important. If you remove all matter, you do not simply reveal an empty stage. You begin to remove the very structure that defines distance and duration. In Einstein's universe, nothing is already less stable than we imagined. But the story does not end there. It becomes even more counterintuitive when we descend into the quantum world. In the early development of quantum mechanics, physicists like Werner Heisenberg uncovered a principle that would permanently alter our understanding of reality. The uncertainty principle does not simply reflect a limitation of measurement. It is a statement about the structure of nature itself. Certain pairs of physical quantities cannot both be precisely defined at the same time. And among these quantities lies something crucial: energy and time. This relationship implies that over very short intervals of time, the energy of a system cannot be exactly zero. Not because we fail to measure it, but because the concept of exactly zero energy loses meaning at that scale. Even in what we would call empty space, there must be fluctuations. Tiny, unavoidable variations in energy that occur spontaneously. At first glance, this might seem like a minor correction. A small technical detail buried deep within the mathematics. But if we follow its consequences carefully, it leads us to a completely different picture of reality. Because if empty space cannot have exactly zero energy, then it cannot truly be empty. This idea was pushed further by physicists such as Paul Dirac, who began to reinterpret the very notion of particles. In modern physics, particles are no longer fundamental objects. They are excitations, localized vibrations of underlying fields that permeate all of space-time. The electron is not a tiny object moving through space. It is a ripple in the electron field. A photon is not a discrete packet traveling through emptiness. It is a vibration of the electromagnetic field. And these fields do not disappear when particles are absent. They are always present, even in what we call a vacuum. So now we arrive at a critical realization. When we imagine nothing, we are often imagining empty space. But empty space, in the language of modern physics, is not nothing. It is the lowest energy state of a system of fields that still exist, still fluctuate, and still obey precise mathematical laws. This state is called the vacuum, and it is anything but empty. Inside this vacuum, something remarkable is constantly happening. Pairs of particles and antiparticles appear and disappear in extremely short timescales. These are not imaginary in the sense of being unreal. They are real consequences of the underlying mathematics, and their effects can be measured experimentally. So what we once called nothing is actually a seething, dynamic structure. A restless foundation where energy fluctuates, fields interact, and possibilities continuously emerge and vanish. At this point, we must confront a shift in perspective that is both subtle and profound. The question, how does something come from nothing, may be incorrectly framed. Because the nothing we imagine does not exist within our best physical theories. Instead, the more precise question becomes, given a vacuum filled with quantum fields, governed by consistent mathematical laws, is it even possible for nothing to remain nothing? And the answer, as far as we can tell, is no. Because the vacuum is not stable in the way classical intuition demands. It cannot sit perfectly still. It cannot remain perfectly uniform. It must fluctuate. And once fluctuations exist, the door to structure opens. At first, these fluctuations are microscopic, temporary variations in energy that vanish almost immediately. But under the right conditions, something extraordinary can happen. A fluctuation does not disappear. It grows. And when that happens, the distinction between nothing and something begins to dissolve. Now, before we move forward, we must be careful not to overstate what we know. Physics does not yet provide a complete, unified theory that explains every aspect of the universe's origin. There are open questions, unresolved tensions, and areas where our understanding remains incomplete. But within the framework we do have, one conclusion stands with remarkable consistency. The universe does not require a transition from absolute nothingness to something, because absolute nothingness is not part of the theory. Instead, the universe may emerge from a state that already contains structure. Not structure in the form of matter or galaxies, but structure in the form of laws, symmetries, and fields. And this is where our journey truly begins. Not from a void devoid of meaning, but from a foundation that is already rich with possibility. We are not asking how existence was created from nothing. We are asking how complexity arises from simplicity. How the quiet fluctuations of a vacuum can, under the relentless guidance of physical law, evolve into stars, into planets, into living systems capable of asking this very question. And perhaps the most unsettling realization of all is this. The universe does not appear to be a fragile accident balanced on the edge of non-existence. It appears to be a natural consequence of the rules that govern reality. Which means that the existence of something may not be the mystery. The real mystery is whether nothing was ever possible in the first place. In the next step of our journey, we will move deeper into this foundation. We will examine the fields themselves, the symmetries that constrain them, and the energy that drives their behavior. Because only by understanding this underlying fabric can we begin to see how the universe builds itself. From nothing, not as an absence, but as a beginning that was never truly empty. We now move forward, not by introducing new mysteries, but by carefully examining the foundation we have already uncovered. If nothing is not empty, if it is instead a structured vacuum filled with fields and governed by laws, then our task becomes precise. We must understand what these fields are, how they behave, and why their behavior inevitably leads to the emergence of structure. Because once we understand the fabric, the appearance of everything else will no longer seem accidental. In modern physics, the most fundamental objects are not particles. They are fields. A field is not something that exists at a point. It exists everywhere in space and time simultaneously. At every location in the universe, there is a value associated with each field. The electromagnetic field, the electron field, the quark fields, the Higgs field. These are not optional ingredients. They are the underlying reality from which all observable phenomena arise. When we detect a particle, what we are actually observing is a localized excitation of a field. A small region where the field is oscillating in a specific way. The particle is not an independent object. It is a pattern in the field. This perspective forces us to abandon a deeply rooted intuition. We tend to think of empty space as a container and particles as things placed inside it. But in the field picture, there is no separation between container and content. The fields are the content, and space itself is defined by their existence. Even if no particles are present, the fields remain, and they are never completely still. At the lowest possible energy state, which we call the vacuum state, each field still possesses what is known as zero-point energy. This is not an added feature. It is required by the structure of quantum mechanics. The uncertainty principle prevents the field from having both perfectly defined amplitude and perfectly defined rate of change. As a result, the field must fluctuate, even in its ground state. These fluctuations are not random in the classical sense. They are constrained by precise statistical and mathematical relationships. But they are unavoidable. We must pause here and recognize the implication. The vacuum is not a static background. It is an active system with internal dynamics. Energy is constantly being redistributed in tiny amounts across spacetime. And although these fluctuations are typically short-lived, they are real enough to produce measurable effects. One example is the Casimir effect, where two closely spaced conducting plates experience an attractive force due to changes in vacuum fluctuations between them. This is not a theoretical curiosity. It is an experimental confirmation that what we call empty space contains physical activity. Now, if fields exist everywhere, and if they are always fluctuating, then the next question becomes unavoidable. Why do these fields have the specific properties that they do? Why these masses, these interaction strengths, these symmetries? And this leads us to one of the most powerful organizing principles in physics. Symmetry. A symmetry, in the physical sense, is not merely a visual pattern. It is a transformation that leaves the fundamental laws unchanged. If a system behaves the same way after a certain transformation, then that transformation represents a symmetry of the system. For example, if the laws of physics are the same at every point in space, we say the system has translational symmetry. If they are the same at every moment in time, we have time symmetry. These symmetries are not aesthetic. They have direct consequences. Through a profound result known as Noether's theorem, each symmetry corresponds to a conservation law. Time symmetry leads to conservation of energy. Spatial symmetry leads to conservation of momentum. These are not separate facts. They are different expressions of the same underlying structure. But the universe we observe is not perfectly symmetric. If it were, nothing would happen. There would be no preferred directions, no variations, no structure. The richness of reality depends not only on symmetry, but on the breaking of symmetry. This is the next crucial step in our understanding. Even if the fundamental laws possess symmetry, the state of the system does not have to reflect it. To see why this matters, consider a simple idea. A system can have multiple possible states that are all equivalent under the laws, but once one state is selected, the symmetry is no longer visible in the outcome. This is called spontaneous symmetry breaking. It is not that the laws change. It is that the system chooses a specific configuration among many possibilities. And this choice creates structure. In the context of the universe, symmetry breaking plays a central role in determining the properties of particles and forces. At extremely high energies, such as those present in the early universe, the fundamental forces may have been unified. But as the universe expanded and cooled, this symmetry broke. The forces separated into the distinct interactions we observe today: gravity, electromagnetism, the strong and weak nuclear forces, each with its own characteristics, each governing a different aspect of physical behavior. One of the most important examples of this process involves the Higgs field. Unlike other fields, the Higgs field has a non-zero value, even in its lowest energy state. This means that the vacuum itself is not neutral. It has a built-in structure. When particles interact with this field, they acquire mass, not as an intrinsic property, but as a result of this interaction. Without the Higgs field, particles would move at the speed of light, unable to form stable structures. The existence of atoms, molecules, and everything built from them depends on this mechanism. At this stage, we can begin to see a coherent picture forming. The vacuum is not empty. It is filled with fields. These fields are governed by symmetries, and the breaking of these symmetries generates the diversity of particles and forces. What we perceive as the complexity of the universe is, at its core, the unfolding of these simple principles. But we are not finished. There is one more ingredient we must consider: energy. Not energy as a quantity stored in objects, but as a property of the fields themselves. The configuration of a field determines its energy, and systems naturally evolve toward configurations of lower energy. However, due to the presence of multiple possible configurations, the system can become trapped in local minima. These are stable states that are not the absolute lowest energy, but are stable enough to persist. This idea becomes essential when we consider the early universe. If the vacuum itself can exist in different energy states, then a transition between these states can release enormous amounts of energy. Such a transition is not gradual. It can occur suddenly, triggering rapid expansion and dramatic changes in the structure of space-time. This is the conceptual foundation that will lead us into the next stage of our journey. Because once we accept that the vacuum has structure, that fields fluctuate, that symmetries break, and that energy can be released through transitions between states, we are no longer asking whether something can emerge from nothing. We are asking how the dynamics of this system inevitably produce complexity. And this brings us to the threshold of a deeper question. If fluctuations are always present, and if certain conditions allow them to grow instead of vanish, then under what circumstances does a small fluctuation become a universe? This is not speculation detached from physics. It is a direct continuation of the principles we have established. In the next step, we will follow these principles to their logical conclusion. We will examine how quantum fluctuations, amplified by the dynamics of space-time itself, can evolve into something far beyond their origin. Not just particles, not just matter, but an entire universe, with structure, history, and the capacity for complexity. We now arrive at the point where intuition begins to fail us completely. Because, up to this moment, we have built a foundation that is internally consistent, Fields exist everywhere. They fluctuate. Symmetries constrain them, and their breaking generates structure. But none of this yet explains how a transient fluctuation, something that should vanish almost immediately, can instead become something persistent, something that does not disappear. This is the threshold where something separates itself from the restless background of the vacuum. To move forward, we must return to a principle we introduced earlier, but now we must treat it with full mathematical seriousness. The uncertainty principle is often described qualitatively, but its implications are exact. If energy and time cannot both be precisely defined, then over very short timescales, fluctuations in energy are not only allowed, they are required. This means that the vacuum is continuously generating temporary excitations. These excitations manifest as what we call virtual particles. They appear, interact, and disappear within timescales so small that they do not violate conservation laws when considered globally. But here is the critical point. The distinction between virtual and real is not absolute. It depends on whether the fluctuation is allowed to persist. Under normal conditions, these fluctuations cancel out. They are local disturbances that leave no lasting imprint. But if the conditions of space-time itself change, the situation transforms completely. To understand this, we must consider that space-time is not static. It can expand, contract, and evolve dynamically. And when space-time expands, something subtle but profound occurs. The scale at which fluctuations exist is stretched. A fluctuation that would normally exist only for an infinitesimal duration can be extended, effectively frozen into a larger structure. This is not an analogy. It is a direct consequence of how quantum fields behave in an expanding space-time. This brings us to one of the most important ideas in modern cosmology: inflation. The hypothesis that in the earliest moments of the universe, space-time underwent an extremely rapid expansion, not just fast in the everyday sense, but exponential, where the size of the universe doubles again and again in incredibly short intervals of time. During this phase, the vacuum itself was in a high-energy state. Not the lowest possible configuration, but a metastable one. And because of this, it possessed an enormous energy density that acted as a driving force for expansion. Now we must follow the logic carefully. If the vacuum has energy, then according to general relativity, that energy contributes to the curvature of space-time. But unlike ordinary matter, vacuum energy has a peculiar property. It produces a repulsive gravitational effect. Instead of pulling space-time together, it drives it apart. The result is not linear expansion. It is exponential. During inflation, space-time doubles in size over extremely short intervals. And as it does, the quantum fluctuations that exist at microscopic scales are stretched to macroscopic dimensions. Fluctuations that would normally vanish are now separated by distances so large that they can no longer cancel each other out. They become imprinted into the structure of the universe. This is the key transition. A fluctuation that cannot recombine is no longer temporary. It becomes part of reality. At this stage, we are no longer dealing with abstract quantum effects. We are describing the origin of structure itself. The tiny variations in energy density created by these fluctuations become the seeds from which all large-scale structures will grow. Regions with slightly higher density will, under the influence of gravity, attract more matter. Regions with lower density will become voids. Over time, these initial differences are amplified. But we must not skip an essential detail. Inflation does not continue indefinitely. At some point, the vacuum transitions to a lower energy state. This process is often described as reheating. The energy stored in the vacuum is converted into particles, not created from nothing in the classical sense, but produced from the energy that was already present in the field configuration. This moment marks the beginning of what we traditionally call the hot Big Bang. A universe filled with a dense plasma of particles, radiation, and rapidly evolving interactions. But now we understand that this is not the absolute beginning. It is a phase transition, a transformation from one state of the vacuum to another. We must pause again and reflect on what has just occurred. At no point did we require an external input, no violation of physical law, no introduction of arbitrary structure. Everything follows from the properties of quantum fields and space-time dynamics. A vacuum that fluctuates, a space-time that expands, a field that transitions between energy states. From these ingredients alone, we obtain a universe with structure. But there is another layer we must examine, because not all fluctuations are equal. The statistical distribution of these fluctuations follows precise rules. They are nearly scale invariant, meaning that fluctuations occur with similar strength across different length scales. This prediction is not arbitrary. It arises directly from the mathematics of inflationary expansion. And remarkably, when we observe the cosmic microwave background, the faint radiation left over from the early universe, we find exactly this pattern. Tiny temperature variations, corresponding to density fluctuations, distributed in a way that matches the predictions of quantum fluctuations stretched by inflation. This is one of the strongest pieces of evidence that this framework is not merely theoretical. It is descriptive of reality. At this point, the distinction between nothing and something has effectively collapsed. What we once imagined as nothing is revealed to be a dynamic system capable of generating structure through its own internal laws. And what we call something is simply the evolved state of that system. We can now state, with careful precision, a conclusion that would have seemed impossible at the beginning of our journey. The emergence of structure in the universe does not require a violation of physical law. It is a direct consequence of it. But we are not finished, because everything we have described so far exists at the level of initial conditions. Fluctuations, expansion, transitions. What we have not yet explored is how these initial conditions evolve into the vast complexity we observe today. Galaxies, stars, planets, chemical elements, and ultimately systems capable of reflection. To understand this, we must now scale up. We must follow these initial fluctuations as they evolve under the influence of fundamental forces. We must examine how gravity amplifies them, how matter organizes itself, and how the simple seeds of quantum uncertainty grow into the architecture of the cosmos. Because only then can we complete the transition from fluctuations to structure, from structure to complexity, from complexity to everything we know. We now take the next step, and it is a decisive one. Because everything we have described so far exists at the level of initial conditions, tiny fluctuations, stretched by expansion, imprinted into the fabric of space-time. But a fluctuation, by itself, is not yet a galaxy. It is not a star, not a planet, not a living system. It is only a difference, a slight imbalance in energy density. And so the question becomes precise. How does a small difference become a dominant structure? The answer begins with gravity. Among all the fundamental interactions, gravity is unique in one essential way. It is always attractive. It does not cancel itself out through opposing charges like electromagnetism. It accumulates. And because of this, even a tiny excess of matter in one region becomes significant over time. A region that is slightly denser than its surroundings will exert a slightly stronger gravitational pull. It will attract more matter. As more matter accumulates, the gravitational pull increases further. This is not a linear process. It is a feedback loop. We must be careful to understand the scale of this process. In the early universe, the density differences were incredibly small. Variations on the order of 1 part in 100,000. And yet, given enough time, gravity amplifies these differences into structures spanning millions of light years. This is not a matter of chance. It is a deterministic consequence of the equations governing gravitational interaction. As the universe expands, matter begins to clump. Regions of higher density grow into what we call dark matter halos. These structures form the scaffolding upon which visible matter accumulates. Although dark matter does not interact electromagnetically, it dominates the mass of the universe, and therefore it dominates the gravitational landscape. Ordinary matter, composed of protons, neutrons, and electrons, falls into these gravitational wells. Now a new process begins. Unlike dark matter, ordinary matter can dissipate energy through radiation. As gas falls into a gravitational well, it heats up. Collisions between particles convert gravitational energy into thermal energy. But this energy does not remain trapped indefinitely. It is radiated away in the form of photons. And as energy is lost, the gas can collapse further. This collapse is the beginning of star formation. A cloud of gas, under its own gravity, contracts. As it contracts, its density and temperature increase. Eventually, the conditions become extreme enough for nuclear fusion to occur. Hydrogen nuclei begin to combine into helium, releasing energy in the process. At this moment, a star is born. We must pause here because this transition is critical. For the first time, the universe contains stable, long-lived sources of energy. Stars are not just objects. They are engines. They convert mass into energy through nuclear processes, and in doing so they alter their surroundings. They produce radiation, they generate heavy elements, and they influence the formation of future structures. Inside stars, a new level of complexity emerges. Through nuclear fusion, elements heavier than hydrogen are formed. Helium, carbon, oxygen, and eventually elements all the way up to iron. But the process does not stop there. When massive stars reach the end of their life cycles, they undergo violent collapses and explosions known as supernovae. In these events, even heavier elements are created. Gold, uranium, and many others. These elements are then ejected into space, enriching the interstellar medium. What we are witnessing is a transformation. The universe is no longer just evolving structurally. It is evolving chemically. The simple composition of the early universe is replaced by a diverse set of elements, each with unique properties. And these properties enable new forms of organization. As generations of stars form and die, the material they produce becomes the raw ingredient for planets. Around young stars, disks of gas and dust begin to form. Within these disks, particles collide and stick together. Small grains become larger aggregates. Aggregates become planetesimals. And through continued collisions and gravitational interactions, full planetary systems emerge. At this stage, we are far removed from the initial quantum fluctuations, and yet every step in this chain can be traced back to them. Without the initial density variations, there would be no gravitational collapse. Without collapse, no stars. Without stars, no heavy elements. Without heavy elements, no planets. The entire hierarchy of structure depends on that original imprint. But we must go one step further, because the emergence of planets introduces environments where entirely new processes can occur. On at least one such planet, chemical complexity reached a threshold where self-replicating systems emerged. This is not a sudden leap beyond physics. It is a continuation of it. Chemistry is governed by the same fundamental laws, expressed at a different level of organization. Over time, these systems evolved. They became more complex, more adaptive, more capable of processing information, and eventually systems arose that could reflect on their own existence, that could ask questions about the universe that produced them. We must now recognize the full scope of what we have described, from quantum fluctuations to conscious observers, from microscopic uncertainty to macroscopic structure. This is not a sequence of unrelated events. It is a continuous process governed by consistent laws. At every stage, the same principles apply. Fields fluctuate. Energy redistributes. Structures form where conditions allow stability. There is no need to introduce external mechanisms at each level. The complexity we observe is the natural unfolding of simple rules over time. And yet, there is something we must not overlook. This process is not inevitable in a trivial sense. It depends on precise relationships between physical constants. The strength of gravity, the masses of particles, the properties of forces. Small changes in these parameters would lead to a universe that evolves very differently. Perhaps one without stable atoms, without long-lived stars, without the conditions necessary for complexity. This does not imply design or intention, but it does emphasize that the structure of physical law is deeply connected to the structure of reality. The universe we observe is not arbitrary. It is one realization of a set of mathematical constraints. Now, as we stand at this scale, we can finally see the full arc of the transformation. What began as fluctuations in a quantum vacuum has evolved into a universe filled with galaxies, stars, planets, and observers. The transition from nothing to everything is no longer mysterious in the way it first appeared. It is a sequence of steps, each governed by well-defined principles. But there remains one final step in our journey. Not a new physical process, but a deeper question about interpretation. What does it mean that the universe can build itself in this way? What does it imply about the nature of reality, about the role of laws, about the place of observers within this structure? To answer this, we must step back once more. Not to abandon the physics, but to see it as a whole. Because only then can we understand what it truly means for everything to emerge from what we once called nothing. We now arrive at the final step of our journey, and it is no longer a question of mechanism, but of interpretation. We have followed the chain carefully, from quantum fields that cannot remain perfectly still, to fluctuations that cannot be avoided, to an expanding space-time that stretches those fluctuations into structure, to gravity amplifying them into galaxies, to stars forging elements, to planets forming, and eventually to systems capable of awareness. At no point did we require a discontinuity in the laws of physics. At no point did we need to invoke an external intervention. And yet, what emerges from this process is a universe of overwhelming complexity. This leads us to a realization that is both subtle and deeply unsettling. The question, why is there something rather than nothing, may not have the form we initially assumed. Because it presupposes that nothing is a valid alternative, that the absence of everything is a stable possibility against which existence must be explained. But throughout our exploration, we have seen no evidence that such a state can exist within the framework of modern physics. What we call nothing is not a neutral baseline. It is not an empty stage waiting for something to appear. Instead, the closest concept we have, the quantum vacuum, is already structured, already governed by laws, already active. It fluctuates. It evolves. It contains the potential for structure. And under the right conditions, that potential is realized. So we must consider a different perspective. Perhaps something does not require an explanation in terms of emergence from nothing. Perhaps it is the natural state of any system governed by consistent mathematical rules. In such a framework, the real question is not why something exists, but whether a state of true nothingness is even definable. We must be precise here. Physics does not yet provide a complete theory that unifies quantum mechanics and gravity. There are still gaps in our understanding, especially at the earliest moments of the universe. But within the domain where our theories are reliable, a consistent picture emerges. Structure arises from instability. Complexity arises from simple rules applied over time. And existence, as we observe it, appears to be a consequence of these principles. There is no indication that the universe required a special starting condition imposed from outside. Instead, the initial state may itself be a natural configuration of the laws, a state that, due to its internal dynamics, cannot remain static, a state that evolves. This brings us to one of the most important insights we can extract from this entire journey. The universe is not constructed in layers, with each level requiring a new explanation. It is continuous. The same laws that govern quantum fluctuations also govern galaxies. The same principles that describe energy and symmetry at the smallest scales also determine the structure of the largest systems. There is no boundary where physics stops and something else must take over. And within this continuity we find our own place. Not as external observers standing apart from the universe, but as systems that have emerged from it. Our thoughts, our questions, our attempts to understand. These are not separate from the physical processes we have described. They are expressions of them. This perspective does not diminish the significance of human existence. It reframes it. We are not anomalies in an otherwise indifferent universe. We are part of the same unfolding process that began with quantum fluctuations. The ability to ask why something exists is itself a consequence of the existence we are trying to explain. There is a temptation, at this stage, to search for a final answer, a definitive explanation that closes the question completely. But physics does not offer that kind of closure. What it offers instead is something more rigorous. A framework in which questions can be refined, assumptions can be tested, and understanding can be extended step by step. In that spirit, we can state our conclusion carefully. The transition from nothing to everything is not a leap across an impossible gap. It is a continuous process governed by the properties of quantum fields, space-time dynamics, and symmetry principles. What we once called nothing is revealed to be a structured dynamic system, and what we call everything is the evolved state of that system. There remains, of course, a deeper question. Why do these laws exist at all? Why this mathematical structure rather than another? This is a question that current physics does not fully answer. But it is important to recognize that this is a different kind of question. It is not about the transition from nothing to something. It is about the origin of the laws themselves. And perhaps the most honest position we can take is this: we do not yet know. But what we do know is already extraordinary. From a set of consistent mathematical principles, a universe can emerge that is capable of forming structure, generating complexity, and producing systems that seek to understand it. Richard Feynman once said, I think I can safely say that nobody understands quantum mechanics. And yet, it is precisely through this incomplete understanding that we have uncovered the deepest structure of reality we have ever known. Not certainty, but clarity. Not final answers, but a framework that continues to reveal new layers of truth. So when we return to the question with which we began, why is there something rather than nothing? We find that the answer is not a single statement. It is an entire structure of reasoning. A realization that the concept of nothing dissolves under careful examination, and that existence, far from being an anomaly, may be the most natural outcome of all. Thank you for staying on this journey. Not just to learn about the universe, but to understand how deeply we are connected to it.